Hello. So last time we discussed Bragg's law, and we agreed that if we irradiate a crystal with an incoming beam of fixed wavelength lambda and making an angle theta with the surface of the planes, we will observe at a detector located far away from the crystal areas where there are bright rings, like we see here. There will be areas where there will be bright rings, and these are corresponding to areas where there is constructive interference, and there will be other areas, gray in color, where there is destructive interference. The condition for constructive interference is known as the Bragg's law, which is 2d sine theta equal n lambda, where n is an integer. One has to rotate the crystal or the counter, that is where I'm putting the crystal, that is a changing theta until constructive interference is achieved. We use the term diffraction in solid state physics to mean that constructive interference took place. When we irradiate a sample crystal with X-ray beams, the beams will get scattered, okay, by the electrons in the atoms that make up the crystal. The intensity of a diffracted beam will depend not only on the amount of scattering a single atom produces, okay, but also on the scattering from the unit cell. In general, the more electrons in an atom, the stronger its interaction with the X-ray is, and the stronger the diffracted beam will be. The intensity of the diffracted beam for any given atom depends on something called the atomic form factor F. Okay, so the atomic form factor, it measures, sorry, it measures the scattering power for some atom in the unit cell. How do we get this atomic form factor? By definition, it's the scattering amplitude at theta, at some angle from the actual electron distribution in an atom, divided by the scattering amplitude at theta g from a free electron, okay? Fj can be derived to be the integral over the nth atom as a function of r multiplied by e to the minus I g dot r, where this g is the reciprocal lattice vector, okay? The scattered amplitude is proportional to the geometrical structure factor. As for diffraction to take place, it's not enough for Bragg's law to be fulfilled. The atomic form factor, this F, should be close to the maximum value for the particular atoms under consideration. Of course, real solids do not consist of only one atom. So in addition, another quantity known as the geometrical structure factor S, which takes place into account the positions of the atoms within the unit cell of the solid, needs to be considered when determining whether diffraction will occur from a particular set of atomic planes. The geometrical structure factor does not depend on where the atoms of a unit cell actually are. It also depends on the atomic scattering factor for the atoms. As G is equal to the summation, depending on how many atoms we have in the unit cell. So if there is only one atom, like in the simple cubic, this will be only one term. If we have two atoms, like in the BCC, this will be two terms, okay? Of this atomic form factor multiplied by e to the minus I Rj dot G, where Rj is the position of the atoms in the lattice in the unit cell. So Rj is xj(a1) plus yj(a2) plus zj(a3). And this G is the reciprocal lattice vector, which is V1, B1 plus V2, B2 plus V3, B3. If I do now the dot product of G dot Rj, I get 2 pi V1 xj plus V2 yj plus V3 zj. Here I have used the fact that B I've used the fact that bi dot aj is equal to 2 pi delta ij, where delta ij is equal to 1 if I equal to j and equal to 0, and delta ij equal to 0 otherwise. That is if I different than j. Okay. And that's how I got that G dot R is 2 pi V1xj plus V2yj plus V3zj. Finally, I get my geometrical structure factor SG V1, V2, V3 is equal to summation over how many atoms I have in the unit cell multiplied by e to the minus I2 pi V1xj plus V2yj plus V3zj. The scattering intensity, that is how bright I see my rings on the detector, depends on this structure value, on this structure factor, and it's actually proportional to its absolute value square. Okay, so we calculate the structure factor and we square it. And this is how much is the scattering intensity. So here we learn that every atom has atomic form factor, and that if we are measuring the scattering intensity, this scattering intensity depends on the geometrical structure factor, whose equation is in this form. Okay. Here is a problem. So find the structure factor of the body-centered cubic lattice. So we start part 1. First, we have to remember that S at any vector J, okay, it's equal to the summation for F J. So S of G is equal to the summation of Fj multiplied by the exponential of minus 2 pi I, or minus I2 pi. So I'll see it easier. Minus I2 pi V1 xj plus V2 yj plus V3 zj. Now for the BCC, I have two atoms, two identical atoms in the unit cell, one at xj, yj, zj equal 0, 0, 0, and another one where xj, yj, zj is equal to half, half, half. So I will get Sg is equal to summation. There will be two terms. Okay, the first term is F1 for the first atom, exponential minus I multiplied by 2 pi into V1 times 0, so that's 0, plus V2 times 0, so that's 0, plus 0. So this is the first term. Okay, plus now the second term, so it is F2 exponential minus I. Again applying this formula. Okay, so there will be two terms. So e to the minus I 2 pi into V1 times half, so that will be V1 over 2 plus V2 over 2 plus V3 over 2. This is equal to F1. What is exponential of minus I times 2 pi times 0? Okay, so this is exponential of 0. plus F2 exponential of minus I2 pi times V1 over 2. So there is half inside. I will get it outside. I will get minus I 2 pi over 2. So that's pi, okay, into V1 plus V2 plus V3. Okay. Now, exponential of 0 is 1. So I get F1 plus F2 exponential of minus I pi into V1 plus V2 plus V3. Now, since I have the two atoms are identical, implies F1 equal to F2, because remember from the definition of the F, it has to do with the atom, with the scattering atom. So if they are identical, then F1 equal F2 equal F. So SG will be F into 1 plus exponential of minus I pi times V1 plus V2 plus V2. So it's a function of the vector G, right? Now, if V1 plus V2 plus V3 is even, I will get SG equal to F into 1 plus e to the minus I pi into an even number. Okay, and this will give me exponential minus I pi even number is 1. So this will give me 2F. Okay, why is this? Because exponential of e to the minus I pi times even number 2 or 4 or 6, it will give me 1. So 1 plus 1 will be 2. If V1 plus V2 plus V3 is odd, I will get SG equal F into 1 plus e to the minus I pi times an odd number. So example to that, for example, is e to the minus 3 I pi or 1 I pi. So what is here? I don't know if you remember. E to the I pi or e to the ix or e to the I theta, it's equal to cosine theta plus I sine of angle theta. Okay. So what do I have here? I have e to the minus I pi. Okay, so this is in case it is odd, for example. This is equal cosine of pi plus I sine of pi. Sine of pi is 0. So it is cosine of pi, which is minus 1. So this is here minus 1. Then I have 1 minus 1 gives me 0. So if V1 plus V2 plus V3 is odd, I get 0 for the structure factor. So this is the case of body center. Let's do the case of face center, face cubic. I'll just read it here. So the basis of a FCC structure referred to the cubic cell has identical atoms at 0, 0, 0, 0, half, half. So the atoms I will consider. So for face center, the atoms I have are at 0, 0, 0, half, half, 0. I have identical atoms at all these places. Half, 0, half, and half, and 0, half, half. Okay. It's very similar to the base to the BCC, except that here I have 4 atoms instead of 2. So I will just read it. So if we come to S, let me just write SG will be F1, or since they are identical, so it will be F, okay, exponential e to the minus I 2 pi into 0 plus 0 plus 0 okay, plus for the second atom it will be F exponential minus, okay, here there should be V1 plus V2 times 0 times 0, so this will be 0, this is correct, plus the second term, so this is the first term for the first atom. The second term will be exponential minus I2 pi, okay, into half V1 plus half V2. So V1 over 2 plus V2 over 2. And then I will get similar ones, e to the minus I 2 pi V1 over 2 plus V3 over 2 plus the last term for the last atom, e to the minus I 2 pi V2 over 2 plus V3 over 2. Okay. Okay, now e to the minus I2 pi times 0 is e to the 0, which is 1. So here I will put 1. Here I have V1 over 2 plus V2 over 2, and I have 2 outside. I will remove the 2 with the 2's. That is, I take half outside, I multiply it by 2, it disappears. And here is the same thing. And it's the same for the last term. Okay, now this is the structure factor for FCC. Now let's take particular conditions. Particular conditions, if V1, V2, and V3 are all even, what do I get? I get V1 plus V2 if they are even, so their summation is even. So I get e to the minus I, even number multiplied by pi. So this will be 1, this will be 1, this will be 1, and there is a 1 here. I get SG is equal to 4. Same thing if V1, V2, and V3 are all odd. Okay, if they are all odd, what do I get? I get SG. So up it was 1 plus 1 plus 1 plus 1 is equal to 4. Now, what will this give me? The first term, of course, multiplied by F. So it's SG equals F into this. So now SG is F into 1 plus V1 plus V2. If they are all odd, take for example 1 and 3. 1 plus 3 is 4. So even if they are odd, their summation is even. So I will also get for everything 1 plus 1 plus 1 plus 1. And this is also for F. Now, if V1 is even and V2 and V3 are odd, implies, what do I get? SG is equal to F into, there is a 1 in the beginning, then V1 is even, but V2 is odd. So take, for example, V1 equal to plus 1. 2 plus 1 is a 3. So this will be minus I 3 pi. This will give me minus 1. Again, V1 is even, V3 is odd. This term is odd. So this will be again minus 1. But V2 and V3 are both odd. So this term is even. The summation is even. So I get plus 1. And this gives me 0. It's the same if I take V2 is even and V1 and V3 are odd, I will get the same thing. SG will be 0 if V3 is even and V1 and V2 are odd. I will get SG is also 0. Okay, so this is the question. Now, in the next slide, I'm asking the question. So let's keep. Okay, we have to move. Another exercise. An FCC crystal can be described by the following 4 sets of atomic coordinates: 0, 0, 0, 0, half, 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 0, half, and half, half, 0. That's what we did in the previous exercise. Is there a Bragg reflection? In other words, a reflection that satisfied the Bragg law from the 1, 0, 0 plane of an FCC crystal? Here by 1, 0, 0, 1, 0, 0 plane, it means HKL is 1, 1, 1. Remember that the reciprocal vector G, which is V1, V2, V3, is the same as G of HKL. Okay, so V1 equal H, V2 equal K, and V3 equal L. Okay, so here he's giving me that V1 equal 1. Okay, it's from 1, 0, 0 plane. So this is 1, 0, 0 plane. So I have V1 equal 1, V2 equal 0, V3 equal 0. Okay, and I want to see if I will get reflection. If I get reflection, implies I will get a value of this as G. That is, when I make it square, I get an intensity. I get scattering factor. Okay, let's see. So remember here when I did the calculation for SG for FCC, I did it up here when the question asked, find the SG for face-centered cubic lattice. Okay, we found the SG to be F into 1 plus e to the minus I pi, V2 plus V3, etc. So I just copied it down here. Okay, now I will put 1 for V1, 0 for V2, 0 for V3. What do I get? I get SG is equal to F into 1 plus e to the minus I pi into 0 plus 0. So that's 0. Okay, plus e to the minus I pi into V1 is 1 plus 0. So it is 1 plus e to the minus I pi V1, which is 1 plus 0, so which is 1 again. Okay, and what is SG in this case? It is F into 1 plus e to the 0 is 1 plus e to the minus I pi is minus 1, and e to the minus I pi is minus 1. So I get SG equal to 0, implies the intensity equal to 0 because it is proportional to the SG square, implies I do not get Bragg reflection from 1, 0, zero plane. Okay, and actually we also concluded that here there is V1 odd and the other two are even. Remember in the previous exercise, we found that if V1 odd and the other two are even, the SG factor will be zero. But here I just did it in another way. Okay, let's move forward. NaCl crystallizes in a face-centered cubic lattice with a basis of Na plus and Cl minus ions respectively at 0, 0, 0, half, half, half. So the sodium is at 0, 0, 0 and half, 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 and this is an FCC-centered cubic lattice with F plus equal 11F, which means F of the N of the sodium ion is 11F, and F of the chlorine ion is 17F. Okay, obtain the structure factor S using the simple cubic lattice with a basis of 8 ions, sodium at 0, 0, 0, half, half, 0, half, 0, half, 0, half, half, and the chlorine at half, 0, 0, 0, half, 0, 0, 0, half, and half, half, half. So we will solve it using the simple cubic lattice, okay, which means I have one unit cell having 8 atoms inside it. Okay, so I will here for the S, I will have the summation of S values. Okay, I'm gonna read it actually because I did it here clearly. So the Sj is the summation over J for these 8 atoms. So I have here the first atom, the second atom, the third atom, and the fourth atom. These are the sodium ions that have F plus, and these are the chlorine atoms. So this is 6, 7, and 8. Okay, this is F plus, so it is for the sodium, and this is F minus, which is for the chlorine atoms. Okay, now for F plus, it's given 11F into, I will just put the atoms. So here I have 0, 0, 0. So it will give me minus I pi. It will give me 1. Sorry, 0, 0, 0 will give me 1. Then I have half, half, 0. So it will give me the second term. Half, 0, half. It will give me the third term. And 0, half, half. It will give me the fourth term. Then for the second one, I do the same. Okay. So I will have 11F into 1 plus e to the minus I pi V1 plus V2 plus e to the minus I pi V1 plus V3. I'm just doing math here, plus e to the minus I pi V2 plus V3. From the chlorine, I will get 17F e to the minus. I actually took this term outside. Okay, I took this term outside. Then what will I have inside is e to the minus I pi V2 plus V3. Okay, because if I divide minus I pi V1 by e to the minus I pi V2 plus V3, I will, by e to the minus I pi V1 plus V2 plus V3, I will get e to the I pi V2 plus V3. Let me show you here. So I have e to the minus I pi V1, okay, and divided by, it means I multiply by e to the I pi V1 plus V2 plus V3, because I took this thing here, e to the minus I pi V1 plus V2 plus V3 as a common denominator. It means I divide each of these by that. If I divide by e to the minus I pi, it means I multiply by e to the I pi. Okay. And this will give me e to the minus I pi Vi disappear. I will get e to the I pi V2 plus V3. And this is what I get here. Okay. And I do the same with the second term and the third term. But e to the I pi V2 plus V3 is equal to e to the minus I pi V2 plus V3. Why is this? Because e to the I pi V2 plus V3 is equal to e to the I pi V2 plus V3 times e to the minus 2 I pi V2 plus V3. This thing over here is 1. Why equal to 1? Because this is an even number, and e to the minus even number times pi is 1. So this is equal to this times this, but this times this is e to the minus I pi V2 plus V3. Okay, so it's the same for the two other terms. So I get S V1, V2, V3. I take common 1. So I have 1 plus this. I will take all this thing here. Okay, so it is 1 plus e to the minus I pi V1 plus V2 plus e to the minus I pi V1 plus V3 plus e to the minus I pi V2 plus V3. It is common here and here. Okay, it is the same term. It's here and here. So I take it as common factor. What I will have inside is now open another parenthesis, 11f plus 17f e to the minus I pi V1 plus V2 plus V3. And this is what I have over here. Okay, now if I look at this, I find that this is exactly what I get for SFCC. If you go back up to the problem where we did the structure factor for FCC, we got it to be f into 1 plus e to the minus I pi V2 plus V3 plus e to the minus I pi V1 plus V3 plus e to the minus I pi V1 plus V2. Okay, and this, what we see over here, is as if I only have the two atoms sodium at 0, 0, 0 and the chloride at half, half, half. Okay, so as for two bases, for a lattice that has a basis, here the basis is not only one atom, it is two atoms, then the S for that will be the S of the lattice. In this case, it is FCC, okay, times S for the basis. But I don't take F twice, I only take F once, because S of the basis is nothing. There is nothing on the basis. There is nothing on the lattice. It is the basis that gives me F. Okay, so let's show this in another way. Part 2 say find the structure X-ray factor for an ACl using the FCC lattice with two ion bases. That is, start with SFCC and then multiply it with S bases. So what is the FCC? We have atoms at 0, 0, 0, 0, half, 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 0, half, 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 0. I calculated that. Okay, this is SFCC. If you go back up to the first problem we did, we got that FCC is F into 1 plus this term. Now for the basis, I have only two atoms. One of them is F plus e to the minus I2 pi by 0, 0, 0. That's where the sodium are. And F minus e to the minus I2 pi into, it is located at half, half, half. So I have V1 over 2 plus V2 over 2 plus V3 over 2. The 2 goes outside, and I will have 11F because it is giving me the question F plus is 11F. And F minus is 17F, e to the minus I pi V1 plus V2 plus V3. Thus, if we look at what we got over here, it is exactly the same as what we got in the previous question over here. Okay, so there are two ways to solve this. If I have a lattice and a basis, there are two ways to do it. If I have all the atoms in the lattice, that is all the 8 atoms, then I can do it as a summation of structure factors coming from these 8 atoms. But if I have the lattice is, for example, BCC, and I have a basis of 2 atoms, then I can do it. I get the S for the BCC, I get the S for the basis, and I multiply them, and then I get the same answer. Okay, part 3 in the question. Deduce the expression for the scattering intensity. Here you just have to remember that the scattering intensity is proportional to this S square. Okay, so we want to do it if V1, V2, V3 are all even. Now I will go to my answer. What is we got? We got this S V1, V2, V3 to be 1 plus all this term. Okay, so if V1, V2, V3 are all even, from here I will get 1 plus 1 plus 1 plus 1 from here, right? So I will get S V1, V2, V3 to be F into 1 plus 1 plus 1 plus 1 into 11 plus 17. This is 112 F. So it is proportional to, I just take the square. Do the same thing if V1, V2, V3 are all odd. So if this term is odd, this is 1. If this term is odd, this is 1. If this term is odd, this is 1. Okay, so I get here 4F from the first side multiplied by 11 plus 17. If V1 plus V2 plus V3 is odd, so here I have minus 17. So I will have 1, 1, 1, 1, 1 into 11 minus 17, which is minus 24F. So the scattering intensity is I proportional to 576 F squared. And the last term is only one of the indices is odd. So for example, take V1 is odd and the other two are even. And you can find the solution over here, but you can try to do it on your own first. That's it for today's lecture.